So, welcome to the next lecture, and we proceed with our discussion of the Parcels Theorem today. Now, in the previous lecture, we had looked at one way of proving the Parcels Theorem, all right. That method involved bringing in the impulse on two dimensions, and in fact, I intentionally used that method of proof to bring in the idea of an impulse in two dimensions, or to relate that particular integral which involved T1 and T2 to the impulse in two dimensions, all right. However, there is a simpler proof, or there is a proof to Parcels Theorem which does not require the use of bringing in an impulse on two dimensions, which I shall now discuss. And my intention in giving various versions of the proof or various proofs to the same theorem is to bring out various aspects of the relation between time and frequency. So, let us look at an alternate proof to the theorem of Parcels. Now, you see, the idea is very simple. In the previous lecture, we looked at a proof which involved replacement of both Fourier transforms in terms of the time expressions. We shall now replace either of them, all right. So, let us begin by looking at the right hand side of Parcels Theorem, which is integral from minus infinity to plus infinity x f y bar f df. And we shall choose to replace only y f in terms of y t, right. So, we will write y f is integral from minus infinity to infinity y t e raised to the power minus j 2 pi f t dt. And we shall make the substitution here. So, the RHS now becomes, as I said, unless otherwise specified, when there is an indefinite integral, we assume, or when the limits are not specified, we will assume the limits span the entire real axis. Yeah? So, I will not keep writing minus infinity to infinity there. Now, look at this expression. Here we have a hybrid integral, one on f and one on t, and under the assumption that our functions are square integrable. We have assumed that our functions are square integrable, that all these integrals converge and so on. Under a wide class of functions x t, y t and the corresponding transforms, it will be valid to interchange the order of the integration. And under those circumstances, the integral on f would act only on these terms. So, we shall take the integral on f inwards and the integral on t outwards. So, let us rewrite it that way. Now, having written the expression in this form, it is very clear if we look at this expression that it is the inverse Fourier transform of x of f, right, and therefore, this is x of t, small x of t, and we have the expression being equated to y bar t x t dt. So, there we have what we wanted. This is the left hand side. Good enough. So, now we have a very neat proof of Parcels theorem, where we do not need to bring in an impulse in 2 dimensions. I could have started with this proof before the other, but I thought it was desirable to introduce that idea before we find that there is a simpler version and we neglect that possibility altogether. All right. So, actually this also illustrates the basic idea behind Parcels theorem. I mean, this, if one goes to the proof, one also understands why Parcels theorem is true. If one looks at the steps, actually it's a very, if you look at it, the result is very simple. Parcels theorem, and in fact, just as I proved Parcels theorem by starting from the right hand side and proceeding towards the left hand side, I could also start equally by using duality by starting from the left hand side and proceeding towards the right hand side. So, let me just illustrate the steps and I leave it to you to complete the argument. So, here we are. Now, we will start from the left hand side, and the left hand side would give us integral x t y bar t dt. Now, here again we use the same idea, we make a replacement of only one of the expressions. So, we replace the expression y t. Y t is replaced in terms of y f. And we make a substitution of this expression in that integral. Now, here again we might interchange the order of the integrals. So, we might take the integral on f outwards and the integral on t inwards, and the integral on t would act on this, which together the integral x t raised to the power minus j 2 pi f t dt is really the Fourier transform of x evaluated at f, and therefore, we have the right hand side of Parcels theorem. So, one can also prove Parcels theorem by starting from the left hand side and proceeding to the right hand side in the same manner. Yeah? So, I leave it to you to complete the details. Now, Parcels theorem has a number of very interesting consequences, and in fact, one wonders whether one should call them consequences or causes. There are so many results in Fourier analysis where the cause consequence is not a very clear relationship. Let me illustrate one such example. Let us invoke duality. Let us invoke duality. If x t has the Fourier transform capital X of f. Then capital X of t has the Fourier transform small x of minus f. Yes? This is duality. The same for y. Let there be a yt which has a Fourier transform capital Y of f, and then capital Y of t would have the Fourier transform small y of minus f. Consider xt convolved with yt. So, we have xt convolved with yt. We have already established that the Fourier transform of xt convolved with yt would be capital X of f into capital Y of f. And if we invoke duality now, we shall have capital X of t multiplied by capital Y of t shall have the Fourier transform given by the convolution of the Fourier transform. Well, you know, it's like this. It is this expression. Now you see, we have to be careful. What is the Fourier, according to duality, what is the Fourier transform of this? It is this expression with t replaced by minus f, right? So, I must write it this way. It is x t convolved with yt with t replaced by minus f. This is the correct statement. But I shall establish that xt convolved with yt with t replaced by minus f is the same as x of minus f convolved with y of minus f. We shall establish that. All right. In other words, we shall in general establish that, you know, if we have an argument, I mean, what I am trying to say is x convolved with y evaluated at minus f instead of f is the same as x at minus f convolved with y at minus f. Now, before we proceed to establish this, what are we trying to get at? What are we trying to establish in this use of duality? We are trying to establish that just as convolution in time translates to multiplication in frequency, multiplication in time translates to convolution in frequency. All right, we are trying to establish that. So, now we shall look at this expression through these derivations. Now, we wish to prove this. Now, the way we proceed is to look at the right hand side first. The right hand side is x1f convolved with y1f, where x1f is defined by x of minus f, and so to y1f. Now, by definition, x1f convolved with y1f is integral x1 lambda y1. Now you see the variable is f. So the argument of the second function would be f minus lambda. Is it right? However, replace x1 lambda in terms of x. So we have, this is x of minus lambda. And y1 at f minus lambda is y at lambda minus f. D lambda. Now please note that the limits of integration here run from minus infinity to plus infinity. If we make a replacement of variable with lambda equal to minus phi, then integral d lambda from minus infinity to plus infinity is the same as integral d phi also from minus infinity to plus infinity. That's because the limits also change, since phi is negative, the limits change from plus infinity to minus infinity and the sign also changes. So d lambda is minus d phi. So if we, combine the negative sign and the interchange of order of limits, then we get this result. All right? So now what do we have? We have this expression becoming integral minus infinity to plus infinity x of phi y of minus f minus phi d lambda d phi. Is that right? But what is this expression? This expression is the convolution of x and y evaluated at minus f. Right? So this is the convolution of x and y evaluated at minus f, which proves the result. Yeah. So, in fact, this is a very general principle that we have established. What is the principle? The principle is that if I time reverse or if I argument reverse both the signals in a convolution. So, if I have two signals, for example, defined on time, and if I convolve them, if I time reverse both the signals and now convolve them, the result will be to time reverse the convolution. But please note, this holds only when we time reverse both the arguments. We had established earlier that if we time reverse one of them, the answer may not be unique at all. So if we time reverse x but not h, it may not be possible to give a unique answer to what the output would undergo as a consequence of this time reverse. So it is only when we time reverse both arguments, both signals in a convolution, that the output is also time reversed, right? But it's a very important principle. Now that's with time, but here we proved the principle in the context of frequency. So if we have two arguments, two signals defined on frequency, and if we convolve them in the frequency domain. Now here the convolution is being done treating f as the independent variable. Now if we happen to reverse or if we happen to negate both the frequencies in the argument signals, then the output also has its frequency negated. Yes, that is what we have established. So, now let us get back to the duality principle that we were using, and let us come to a conclusion. We had shown that if xt convolved with yt it is known that xt convolved with yt has the Fourier transform xf into capital Yf, where capital X and capital Yf respectively are the Fourier transforms of small x and small y. Now, we have said that by duality we establish capital Xt into capital Yt has the Fourier transform small x convolved with y evaluated at minus f. That is the conclusion that we can draw out of duality, right. But now, with our derivation over the past few minutes, we can also conclude that this is equal to x of minus f convolved with y of minus f. Is that right? Yeah. But what is x of minus f? X of minus f is the Fourier transform of capital X of t, and small y of minus f is the Fourier transform of capital Y of t. And therefore, what we are saying is that the Fourier transform of the product of these functions, capital X of t and capital Y of t, the Fourier transform of this product is the convolution of the individual Fourier transform. This is a general conclusion that we may draw. Yeah? So, the Fourier transform of a product this is the conclusion that we have drawn. Yeah? A beautiful conclusion because it is exactly dual to the idea of convolution. Yeah? So, it shows the symmetry between time and frequency. I must also emphasize that this clearly illustrates that if I multiply a signal in time with another signal in time, the Fourier transform is not simply scaled. Now, it is obvious when what I mean is the Fourier transform is convolved with some other Fourier transform. Now, this is a very common pitfall. For example, we are very prone to thinking, particularly for very simple functions of time, that if we multiply xt by a very simple function of time, the Fourier transform is simply scaled or multiplied by some other function of f. Now, when I put it so explicitly, it quite clearly is erroneous, it quite clearly appears to be erroneous, but subconsciously a beginner tends to make this mistake in his derivations or in his or her arguments. So, I thought I should caution the audience right at this point. Now, some more interesting properties of the Fourier transform. Well, actually, the first interesting property is what is the consequence of this at zero frequency, right? So let's write this statement down. Let's write this statement down in mathematical language. Integral xt yt e raised to the power minus j 2 pi ft dt. This is the Fourier transform of the product of xt and yt. Yeah. Is the convolution of their Fourier transform. So, capital X evaluated at lambda, capital Y evaluated at f minus lambda d lambda. Now, please note that I have chosen in this whole discussion to use the variable f instead of the variable omega. That is because f allows you complete symmetry. With omega, you need a factor of 2 pi. One can write down all these arguments in terms of the angular frequency omega as well. And maybe it is a good idea to also do that as an exercise. Because, it is helpful sometimes to write the arguments in terms of omega and sometimes to write them in terms of f. It is easier to begin by writing them in terms of f because there is perfect symmetry, but at times one needs to write them in terms of omega. It is a very simple change. All that one needs to do is to write f is omega by 2 pi and make the appropriate changes. In any case, what is the consequence of this at f equal to 0? This gives us x lambda y minus lambda d lambda. Now, does this remind us of something? In fact, at f equal to 0, this tells us that, this would be equal to this. Now, does this ring a bell in our minds? This is essentially a version of Parcels Theorem. We could think of yt as the complex conjugate of some other signal, or we could apply the Parcels Theorem on xt and y bar t. Right? We could apply the Parcels Theorem on xt and y bar t. So, xt y double bar t dt is equal to x lambda, the Fourier transform of y bar t complex conjugated d lambda. So, you would find that this in fact is just a statement of the Parcels Theorem for xt and y bar t. So, one apparent consequence of what we call the theorem of multiplication, the previous theorem that we discussed, where we said that a product of signals results in the convolution of their Fourier transforms, could be called the multiplication theorem, just as we call, the principle that if you convolve two signals, their Fourier transforms are multiplied as the convolution theorem. We could call this the multiplication theorem. So, one consequence of the multiplication theorem seems to be the Parcels Theorem. Yeah? It appears to be. Why I say it appears to be is, as I said earlier, in Fourier transforms it is very often difficult to put down a cause and consequence relationship. We shall now show that we could also think of the multiplication theorem as a consequence of the Parcels Theorem. Well, consider this quantity. What is this quantity? This is the Fourier transform of the product xt and yt evaluated at f equal to f0. Yeah. Now I could rewrite this. I could think of this as xt g bar t dt. Where gt by definition is the complex conjugate of the second argument there, yt e raised to the power minus j 2 pi f0 t dt. I am sorry, there is no dt here. Of course, certainly nothing very special about this. So, this can be written as y bar t e raised to the power j 2 pi f naught t. Now, suppose we invoke Parcels Theorem this time. Then integral xt g bar t dt would be the Fourier transform. So, it would be capital X of f, capital G of f bar df. So, we need to find capital G of f. We need to find capital G of f. Now, capital G of f by definition is integral y bar t e raised to the power j 2 pi f0 t e raised to the power minus j 2 pi f t dt. And we might rewrite this as a complex conjugate again, a complete complex conjugate. Is that right? Is that correct? Yes. So, this is nothing but capital Y. So, you see nothing. What is this really? It is the Fourier transform of Y evaluated at f minus f naught. Or rather, it is the Fourier transform of y evaluated at f naught minus f. So, in fact, maybe it is more convenient for us to write it this way. Let us write it this way. It is the same expression, but it brings into evidence the fact that it is the Fourier transform of y evaluated f naught minus f, complex conjugated. Yes, Thiel.
Capital G should not be Fourier transform
capital G of f is the Fourier transform of g of t. So, g of t is this. Capital F is the capital G of f is the Fourier transform of small g of t, and small g of t is defined this is obtained this way. Is that right? So, therefore, is that fine? So, is the argument clear so far? Yeah. Now, let us use this principle. So, now what does Parcels theorem tell us? Well, it tells us that, so this is g of f. Let us keep this available for ourselves. And we have integral x t g bar t dt, which is the same thing as x t y t e raised to the power minus j 2 pi f 0 t dt is equal to integral x f g bar f df but now if we substitute for gf from here, we shall have xf y of f 0 minus f df, and lo and behold we have the same conclusion. Yeah, the Fourier transform of x t y t evaluated at f 0 is the convolution of the Fourier transforms of x t and y t, namely capital X and capital Y, evaluated at f 0. So, it is interesting. We said the Parcels theorem earlier was a consequence of the multiplication theorem. Now, we also find it is a cause, right. So, the cause consequence relation is not always very one sided in Fourier transforms. One might think of any one of them as the cause and the other as a consequence, right. Now, we shall look at some more consequences of the Parcels theorem, or if you wish, you may even want to call them causes, and I leave it to you to establish the duality there. Let us look at the Fourier transform of the following, or let us look at this product x t or let us write as x t plus tau x t. X t bar dt. Or for that matter, let us in general take a y t first here. So, let us look at this product. Now, this product has a very great significance in signal processing, in dealing with signals and systems. It is called the cross correlation of x and y evaluated at tau. It is called the cross correlation. Of x and y, and it is often denoted by Rxy, evaluated at tau. Why correlation? What are we doing here? We have taken a shifted version of x and we found its dot product with y. That is what we have done. Think of x as a vector, y also as a vector, and therefore a shifted version of x also as a vector. We are finding a dot product between various shifted versions of x and y. So, it is like finding out the commonality or the projection of different shifted versions of x onto a different signal y as a function of the shift. That is what cross correlation means. This idea is very important. For example, it is very important in digital communication. When we wish to detect or when we wish to recognize an incoming waveform in the presence of noise, or in a number of other situations where we wish to recognize the presence of one or more waveforms in a clutter, we use the idea of cross correlation. So, let us use Parcels theorem on this, right. What does Parcels theorem tell us? It tells us that this would be equal to the Fourier transform of x t plus tau. But what is the Fourier transform of x t plus tau? The Fourier transform of x multiplied by e raised to the power j 2 pi f tau. Right? When we shift on the time axis by tau, we multiply the Fourier transform by e raised to the power j 2 pi f tau. So, we have x f e raised to the power j 2 pi f tau times y bar f df. That is what Parcels theorem tells us. But look at the right hand side, look at this expression. Can we reinterpret this expression? Can we write it as integral x f y bar f e raised to the power j 2 pi f tau df? Can we write it this way? It is a simple rearrangement. Now, this is a function of f, all right. And what does this tell us? What are we saying here? This is the inverse Fourier. If you think of tau as a time argument now, this is the inverse Fourier transform of x f y bar f evaluated at tau. So, if you think of this as a function of tau, tau is like a time argument. So, if you think of this as a function of tau, yeah, the Fourier transform of this must be x f into y bar f, because you are saying this is the inverse Fourier transform of x f y bar f. This leads us to the conclusion that R x y tau has the Fourier transform x f y bar f. Now, one can come to the same conclusion by using a version of the multiplication theorem or the convolution theorem. Yeah, one can come to the same conclusion by using, you have a product of Fourier transforms here, so you can come to a similar conclusion by using a version of the convolution theorem. Yeah. So, we shall proceed from this point onwards in the next lecture.